Welcome to Brain Vision.
Hi everybody, so we need to know how much energy is released contained in 1 kilogram and if it's a natural deuterium. Okay, so for this, we have the equation of the deuterium plus deuterium equal in reaction to 3 hydrogen plus hydrogen. And this has an energy of 4.0. I believe I wrote 4. This is why I need to read my handwriting, guys. Don't be like me. NEV. There we go. And for this, we need to find the natural abundance of deuterium, and they gave us 0.0115%. So we need to know how much that's in there. So we have 2 times 0.000115 times mass. We have 1,000 grams times Avogadro's number, so 6.023 times 10 to the 23rd mole, divided by 18 grams per mole. Okay, and that's going to be 7.7 times 10 to 21. And so we have 2 deuterium. So we have 2 deuterium. So what we do is take 7.7 times 10 to the 21 and divide it by 2. So we end up with 3.85 times 10 to the 21. Okay. Now we need to find the energy released. So we have 3.85 times 10 to the 21 times the 4.03 megavolts that we had in the appendix. And that's going to equal to 1.55 times 52. There we go. 52 times 10 22 MeV. And we need to convert this to joules. So we have that 1.55 times 10 to 22nd power MeV times 1.6 times 10 to negative joules in EV. Okay. And then we end up getting 2.48 times 10 to the 6 joules. Okay. Thank you guys. I hope that helps.
Welcome to Brain Vision. Welcome to Brain Vision.
Now we are given alpha particle with a dose of 350 rads. Now we want to find what is the same amount of X-rays that will give the same amount of biological damage. Now we know that alpha particle has an RBE, or relative biological effectiveness, of 20. So it means that it is actually 20 times more effective in inducing damage compared to X-rays, right? Where X-rays RBE is actually only close to 1. So it means that we will need 20 times as much of X-rays in order to get the same amount of damage as alpha particles. And that will mean that the rads that is required, or the dose that is required, will be 350 times 20, which we should get 7,000 rads. So this is the amount of X-rays that's required in order to produce the same biological damage as 350 rads of alpha particle.
Welcome to Brain Vision.
In this question, we are comparing slow neutrons to fast neutrons. Now, first off, you need to understand biological damage. And biological damage is actually can be kind of represented by the effective dose, where the effective dose is equals to dose in terms of grays or rads, right? Rads multiplied by RBE, right? The relative biological effectiveness. So we want to find what is the amount of rads for slow neutrons and compare it with the rads, 72 rads of fast neutrons. And want them to have the same effective dose, right? Same biological damage means same effective dose. We know that from table 31.1, the RBE for slow neutrons, right? For slow neutrons is 5, but for fast neutrons it's 10. So they have a slightly different RBE, right? So what we have to do is to simply equate the dose multiplied by the RBE to be equal to each other. So the dose we are given for the fast neutrons is 72 rads multiplied by the RBE, which is 10, must be equals to the dose for the slow neutrons multiplied by 5, right? Because we want the same effective dose, which is equal to saying we want the same biological damage, right? So the amount of dose that is required for the slow neutrons in order to get the same amount of biological damage, we just bring the 5 over to the left hand side. Gets 144 rads. So this is the dose that is required to get the same amount of damage.
Welcome to Brain Vision.
For this question, basically we are converting from sieverts to dose. Now we first need to understand the relationship, right? So sieverts is equals to dose multiplied by RBE, right? Where dose is in terms of gray, RB is dependent on the type of radiation. And in our case, we are looking at gamma rays. So for gamma rays, the RBE is equals to 1. And so this means that the service is equivalent to the dose in gray. Right? So no difference. So in this particular case, we are given 4 sieverts of gamma rays. It will mean that the dose is 4 grays.
Welcome to Brain Vision.
So we are given a dose of 2.5 grays that is being absorbed by a 65 kilogram adult. Now we know that dose is defined as joules per kilogram in terms of gray, the unit gray. So in order to find what is the energy, right, the total energy, we just multiply by the mass, right, kilogram. So 2.5 joules per kg multiplied by 65 kg, and we get 162.5 joules, right, which is approximately 160 joules.
Welcome to Brain Vision.
In the first part of this question, we want to convert from effective dose into absorbed dose. So we know that effective dose basically is equals to absorbed dose multiplied by the RBE. Now in this case, we're going to assume RBE is approximately 1. In actual fact, it's about 1.1, but we're going to assume RBE for protons is 1. So we can actually equate the absorbed dose to the effective dose. Right, so 1 REM would be equivalent to 1 rad. Right, so the absorbed dose is equals to 1 rad. Right, or you can leave it in terms of grays, which is we divide this by 100, and this would be 0.01 grays. Now to find out how many protons, right, are being absorbed by the tumor, we are given that each proton has an energy of 1.2, right, energy per proton 1.2 MeV. Alright, we convert this into SI units, joules, by multiplying by 1.6 times 10 to the power minus 13 joules per MeV. Now we know that the absorbed dose, given over here, the grays, is defined as the energy absorbed per unit mass. So we can convert what is the total energy that is absorbed by the tumor by multiplying the absorbed dose, which is 0.010 grays, multiply that by the mass of our tumor, which is 0.2 kg, to get the total energy absorbed in terms of joules. Finally, you can get the number of protons by taking the total energy absorbed divided by the energy per proton, right, to estimate what's the number of protons absorbed by the tumor. So putting everything in, And putting it into the calculator, we should get a value of about 1 times 10 to the power 10 protons.
Welcome to Brain Vision.
Now we're given a source of phosphorus 32 with an activity of 0.035 microcurie. We want to find what is the number of counts that the Geiger counter will count, right, or intercept. But we are given that the Geiger counter only intercepts 35% of all the emitted particles, beta particle, and furthermore, the efficiency of the Geiger counter is only 85%. Right, so the total number of counts or total number of activity that is counted is actually 35% times 85%. Right, so that is 0.35 times 0.85 of the total activity. Right, so the counting rate P equals to the activity multiplied by 0.35 times 0.85. But right now our activity is in terms of microcuries. We have to convert that into decays per second by converting that into becquerels. Right, so what we do, we're gonna take 0.035 times 10 to the power minus 6. Right, this in terms of curies, and then we multiply that by the conversion factor from curie to decays per second. That is 3.7 times 10 to the power of 10, and we should get decays per second. Right, so we just substitute that into this equation. So that's the activity. Right, this is the activity in terms of decays per second, and then this is due to the different efficiencies of the Geiger counter, and so our counting rate would be about 390 counts per second.
Welcome to Brain Vision.
Now the basic idea of this question is to relate the two different definitions of Röntgen via the idea that the energy required to produce an ion pair is equals to 35 eV. Right, we want to see whether this will be able to relate the two definitions of Röntgen. Now the first definition is that 1.6 times 10 to the power 12 ion pairs are produced per gram of material, or when we have one Röntgen. The other definition is that the other definition would be a total energy deposited of 0.878 times 10 to the power minus 2 joules per kg. Right, is similar, right? Same, also one Röntgen. Now to relate the two together, we start off with this particular definition of Röntgen. We convert from kilograms to grams, right, by dividing by 1000. So that is multiplied by 1 kilogram. gram per 1000 gram. And then we convert from joules to EV, right? Since our ion pair energy is in terms of EV, gonna divide by 1.6 times 10 power minus 19 joules per EV. Finally, we can convert from EV into ion pairs by dividing by 35, since each ion pair takes up 35 EV. Putting it into the calculator, we should get a value of 1.567 times 10 to the power 12 ion pairs per gram, right? Which is quite similar to our first definition. So if you were to just check how close they are, right, it's by taking the difference, right, taking 1.6 minus 1.567 divided by 1.6 times 100%, we see that they are about 2% different from each other. So the value of 35 EV is consistent, right, with our two different definitions of Röntgen.
Welcome to Brain Vision.
Now to start this question, we're gonna approximate or make the assumption that our decay rate is constant, right? That is the given as the 1.6 millicuries, right? This is the activity that we are given. Now with this particular decay rate or the activity, we should be able to find what is the dose rate. We're given that 1 millicurie delivers about 10 milligrays per minute, so this will be about 16 milligrays per minute. And using this dose rate, we can find what is our time that is required, and we need to compare what is the time required with the half-life, and if it's much smaller than the half-life, then this assumption is valid, right? This assumption that the decay rate is constant will be valid, but if not, then we will have to do a further step of using a variable decay rate, right? So for this case, we're gonna just assume the simpler version first, which is a constant decay rate. We have this amount of dose rate, so the time required be the total dose required, which is 32 grays, divided by the dose rate, so that's 16 times 10 to the power minus 3 grays per minute. We should get our answer in terms of minutes. So about 2000 minutes, which is in terms of days, we divide by 1440 minutes per day. We should get a value of about 1.4 days, and this is actually much smaller than the half-life given, which is 14.3 days. So the time required is about 10% of half-life, t half. So our initial approximation that the decay rate is constant is valid and reasonable. And so this will be the approximate time required for the dose to be delivered.
Welcome to Brain Vision.
Now in this question we have a person that accidentally ingested 1.55 microcuries, activity 1.55 microcuries of cobalt 57. So this is the activity. We're going to assume that this is constant throughout the day. And to find what is the dose rate for the whole body, we are given that 50% of the energies are absorbed. So the energy per gamma ray is 122 keV. First, we'll need to find what is the total number of rays that a person will receive over the day, right? So total number of gamma rays. We take the activity, which is 1.55 times 10 power minus 6. We convert that curies into decays per second. So this is the conversion factor. Then we multiply by the number of seconds in a day. So that's 24 times 3600. So this is the total number of gamma rays that will be released in the body. Now the energy that will be deposited, total energy deposited, we take the total number of gammas multiplied by 122 keV divided by 2. Since we are given that only 50% of the energy is deposited into the body, then finally we can get the dose, which is given as the energy per unit mass. Right, so we take energy deposited divided by the mass of the person, which is 65 kilograms. So I'm gonna put everything together. Now the only issue over here is that energy in terms of keV have to be converted into joules, since the dose is actually in terms of joules per kg. So to convert from keV to joules, we multiply an additional factor of 1.6 times 10 to the power minus 16 joules per keV, right, to convert to joules. Our final answer would be 7.4 times 10 power minus 7 grays. So this is the dose that is absorbed per day over the entire body of the person. So the dose rate is simply 7.4 times 10 to the power minus 7 grays per day.
Welcome to Brain Vision.
Now to write down the decay for our iodine 131, we need to first look up Appendix B to find out what is the mode of decay. And the appendix tells us that iodine 131 decays by beta decay. So it emits a beta minus particle. And then we have the anti-neutrino, and we have our unknown X. So we want to identify what's this unknown. We should be able to by just looking at the proton number and the nucleon number, so they must be conserved. So since the beta minus has a proton number of -1, X must have a proton number of 54, so that the total proton number is 53. Same thing with the nucleon number, it must be 131. So X, looking up the periodic table for an element with 54 protons, we should identify this as xenon. So it is xenon. So this is the decay equation. Now we are given an unknown amount, say activity or number of nuclide to be N0, and we want to find how long it will take for N0 to decay to 5%. 5% of its original value, so that is 0.05 times N0. We're going to use the decay law, that is the value n at any time after N0 is given as N0 times e exponential to the power of negative lambda t. T is the time, right, that we want to find. Lambda is the decay constant, which is given as ln 2 over t half, where t half we are given to be 8 days. So ln 2 over 8 days. All we need to do is we divide, or we cancel away N0 from both sides of the equation. Then we take the natural log of both sides. We should get negative lambda times t we bring the expression over to the left hand side to get our answer in terms of t. We should get a value of about 34.58 days, which is approximately 35 days. Now we are given another amount of iodine where the activity is 1 millicuries, or 1 times 10 power minus 3 curies. We want to find out what is the mass of iodine. To find the mass, we need to find what is the number of nuclides, and then we can find the mass. So the activity is defined as the decay constant multiplied by the number of nuclides. So we can get our number of nuclides by simply knowing the lambda. So from previous page, we already know that lambda is ln 2 over 8 days times n. But in this case, we need to convert the days to seconds, right? Since curies, we're going to convert later into decays per second. So what we have to do is multiplying 8 days by the number of seconds in a day. That's 24 times 3600. So this will give us in terms of seconds. Now we just need to convert our activity from curies to decays per second by multiplying by 3.7 times 10 power 10 decays per second per curie. So we can finally find what is our number of nuclides by bringing the entire expression over here, right, this expression, to the activity, right, divide it over. So we should get 1.0 times 3.7 times 10 to the power 7 divided by ln 2 multiplied by 8.0 times 24 times 3600. You should get a value of 3.69 times 10 power 30. So this is the number of nuclides, of iodine nuclides. To get the mass, we take the number of nuclides divided by Avogadro's constant, which is 6.022 times 10 power 23. This will give us the number of moles, and then we multiply by the molar mass, which is 0.131 kilograms per mole, to give us the mass in terms of kilograms. This will be 8.0 times 10 to the power 12 minus 12 kg. So with the particular activity 1 millicurie of iodine, we will need a mass of 8 times 10 to the power minus 12 kilograms of the iodine.
Welcome to Brain Vision.
For this question, we are looking at what is the dose a person will receive from drinking milk. Right, so we want to find what is the total dose received by the person in a year due to the milk. Start off with a single day first. So for a single day, the person we are given drinks 0.5 liters of milk. And from this 0.5 liters, we know that the activity is 2000 picocuries, which is 2000 times 10 to the power minus 12 curies per liter. And from this curies, we need to convert into decays per second. So this number of decays per second per curie. But for each day, we need to find out how many seconds there are, right? Multiply that by the number of seconds per day, which is 24 times 3600. But we are given that only the milk only stays in the body for 12 hours, right? So for each day, it should be only 12 hours. So considering only 12 hours a day, and this will give us a total of 1598 times 10 to the power 6 decays per day in the person's body, right, due to the milk. Next, we can find what is the energy that is being absorbed by the person per year, right? From here, we move on to a year. So the energy absorbed in a year, we take the number of decays in the day, multiply that by the number of days in a year, that is about 365, right, 365 days, and then we multiply that by the energy that's released per decay, that is 1.5 MeV, but we are given that only 10%, right? 10% of this 1.5 MeV is absorbed by the body. So we gotta multiply that by 10%. Next, we want to convert MeV into joules, right? Because dose is in terms of joules per kg. So we multiply this MeV by 1.6 times 10 to the power minus 13 joules per MeV to get our answer in terms of joules. You should get 1.4 times 10 to the power minus 5 joules. So this is the energy that's absorbed in a year. Now we want to find out what is the dose for an adult versus a baby in terms of REM. So REM, basically we have to take the dose in terms of rats, multiply that by the RBE, relative biological effectiveness, which is dependent on the type of radiation that we're looking at. But for our potassium, right, the radiation type is basically gamma and beta, and so the RBE is 1, right, for gamma and beta. So basically REM is equivalent to rads, right? It's the same. There's no conversion factor that's needed. So what we need to do now is to find the dose. We have already the total energy that will be absorbed by the body. We just take the energy, which is 1.4 times 10 to the power minus 5 joules, divide that by the mass, which is 60 kilograms. This will be in terms of grays, but we have to convert from grays to rats, right, or millirats. So to convert from grays to millirats, we have to multiply by 100, 10 to the power of 5 millirats per gray, which is in terms of joules per kg. Right, and since we are already given that rad is equals to REM for this case, we don't have to do any conversion factor, right? The 1 millirad should be the same as 1 REM, 1 milli REM. Right, and we should get a value of 2.33 times 10 to the power of minus 2 milli REM per year, compared to the limit of allowed dose, that is 100 milli REM. This is much smaller, right? So it's not very significant for an adult. Now we do the same process, but now for a baby, a 6 kilogram baby. The same amount of energy is being absorbed, but the mass of the baby is only 6 kilograms. And so the answer that we get is actually quite different. It is about 0.2 milli REM per year, which is much closer to the allowed dose as compared to an adult, right? So for the adult one, we take 2.33 times 10 to the power minus 2 divided by the allowed dose, which is 100. We get about 2 times 10 to the power minus 4. So this is about 2 times 10 to the power minus 4 times of the allowed dose. Whereas for the baby, it is 0.2 divided by 100, which is about 2 times 10 to the power minus 3 of the allowed dose.